Hey, what's up, everyone? How are y'all? Continue.
I have a quick Achieve question.
Sure.
So I'm doing one of the homeworks today, and I completed an entire problem, and it told me like check, 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 like everything's done.
Mm-hmm.
But it only gives me like 98% out of 100 on the question, and I don't know.
98%. That's the homework and not the learning curve?
No, it's the actual homework itself, because like it shows you what you got for each question. Like it's somewhere like half points and like the different parts. And this one's 3 parts, and I have all 3 parts done. I've checked it like 3 or 4 times. I've got off of Achieve, got back on to Achieve, and it only shows me having 98.3% of it.
Shoot me a Canvas mail and I'll look at that. That's strange. I'll take a look at it.
All right, thank you.
Okay. Okay, so a couple things. So first of all, I've uploaded some more practice problems. So these are more up-to-date practice problems that were created by the current course coordinator who is writing this exam. So I've uploaded those to files in Canvas. In fact, let me make its own section. Yeah, okay. So it's under files in the folder exam review questions. So there are not currently solutions for those, but I will either see if I can get those from the course coordinator, or if not, then I'll post those this weekend. But I would do those first because those are going to be closer to the types of questions you're going to get on this exam. Yeah. And so number two, so we'll be having the review on Monday. So I guess we should figure out now whether or not, whether we want to do it like directly after class or more towards the evening, say 5 to 7. I'm actually leaning towards directly after class, and I think I might actually do that. Yes, so I'm gonna send out an email over the weekend with all that info. Terrell. Yeah. So I'll be sending out some emails with everything you need to do, like the whole process and what all you need to do for that. Yeah, I will make sure to send those out. But yeah, look over those review questions, and I will see if I can get the solutions to those over the weekend. So yeah, let's just say that I'll be holding the review session directly after class on Monday. So Monday, yeah, I think that's probably the best bet. So Monday, in fact, I think I'm just going to extend the lecture for an hour, and I'll just continue answering questions, working out stuff, that sort of thing. So the way I usually do this is, I mean, if you have anything you'd like me to talk more about, any specific subjects, or any exam review questions you'd like me to work out, then I'll do that. But it's not going to be like me coming prepared with a bunch of review stuff. It's going to be you guys tell me what you need help with, and then that will be what guides the review session. So make sure you take a look at as much of the review questions as you can, including some of the older stuff on the Math 230 website. And I will be answering that or going through that stuff on Monday. And yeah, I'll probably extend class for another hour or a bit, and then I'll put that up on YouTube, and that'll be the review. Yeah, and then maybe I will have, so normally I would have office hours on Monday right after class, but I think I'll just move those office hours to 5 o'clock, let's say. Yeah. So let me write that down. That's what I'll do. And if you have more questions, you can come to office hours. Sound good? Okie doke. So let's look at the last bit of stuff that will be on this midterm. Okay. So this is, we're going to cover motion in space. So motion in 3 space. So we've already kind of covered this stuff, but this is just going to be more focused on motion type problems. Okay, so we've seen that we can parameterize curves in space with vector functions. So a vector function r of t. So we can think of the vector function r of t as giving position of a particle moving. So think of a particle moving along a curve in space. So when we parameterize it, r of t is going to give the position at time t of some particle on your curve. So r of t gives position. And we saw that r prime of t is going to be a tangent vector. And in fact, it's going to give velocity. So it's going to be the velocity of your particle, right? It's going to be tangent to the curve. It's going to be pointing in the direction of travel. So it's going to point in the direction of travel at time t. And the magnitude is going to be the speed. And we're going to write that as sort of cursive v of t, but not a vector because it's magnitude, and magnitude is a scalar. So r of t gives position. R prime of t is going to be velocity, and we'll often write it as the vector v of t. And the magnitude of r prime of t is going to be speed, right? Magnitude of velocity is speed. And we're going to write that as sort of cursive v of t. And then, of course, we haven't talked about it, but r double prime of t, which is, of course, since r prime of t is v of t, r double prime of t is just the derivative of velocity. And what's the derivative of velocity? Well, that's acceleration. So we'll often write that as a of t. So RT's position, r prime of t is velocity, and r double prime of t is the rate of change of velocity or acceleration. Okay, so some problems will give you r of t and say, you know, find the speed at time t equals 1 or something like that, or find the acceleration. That's really easy. All you're doing is you're taking derivatives and you're plugging in a time. You're not going to see something like that easy on an exam, for instance. More likely, you're going to see something along these lines. We're going to go the other way, in fact. So suppose what we know is instead we know acceleration. So suppose acceleration is cos t e to the t t. And suppose we know two other bits of information. We happen to know velocity at a specific time, usually 0. So initial velocity is I. Remember, I is just 1, 0, 0. And initial position, so the position at time 0 is k, which is 0, 0, 1. Okay, so instead of starting at position, r of t, and taking derivatives to find acceleration and velocity, we're going to start at the bottom at acceleration and with a couple other bits of info, find position. Okay, so how do we do this? Well, we know if we have position, so if we want to go from position, if we know position and we want to find acceleration, let me actually do that on the other side. Well, to go from position to velocity, we take the derivative. And to go from velocity to acceleration, we take the derivative again. So to go from position to acceleration, we take the derivative twice. Right? But we're losing information every time we take the derivative. So, right, so if you have, was this stuff in the homework due tonight? The stuff we're talking about right now? They probably had some velocity related stuff in those, but not this specific. It's like very, okay. Then this might answer some questions, but you should be able to do those problems without specifically knowing what we're talking about today. But yeah, this might clear some stuff up. So when you take the derivative, you're losing some information, right? Every time you take a derivative, you kill off constants in a function, right? And then similarly, if you know the velocity at 2 points, you could have the same velocity but be in different spots. You don't have information about where you're actually located with velocity. And similarly with acceleration, you can know the acceleration, but you don't know actually what your velocity is at a given time necessarily. And so that's why we need these other bits of information here. Okay, so we start off at acceleration. So to go from position to acceleration, we take the derivative twice. To go from acceleration to position, we have to undo the derivative. And what's the opposite of a derivative? Well, we take the integral twice. So we're going to do the indefinite integral twice. And we need these extra bits of information here because when we take the indefinite integral, we have unknown constants that we need to solve for. Because you can't have an unknown constant in your position function. It needs to be all definite values. And so we're going to use those bits to find the value of the unknown constants. Okay. All right. So first, we need to find velocity. So we know velocity is the integral of acceleration because acceleration is the derivative of velocity, so we need to undo that. So that's the integral of cos t e to the t. And so it's the indefinite integral. So what we do is we take the indefinite integral of each component separately. So when we integrate cos t, we get sine t plus some unknown constant. When we integrate e to the t, we get e to the t plus some other unknown constant. And these are different unknown constants, so use different C1, C2, and C3 for these. And then when we integrate t, we get 1/2 t squared plus some third unknown constant, C3. So we know velocity, but we have these unknown constants that we're not sure about. And that's where this bit comes in, the initial velocity. So we know most of the function of velocity, and we know velocity when we plug in a specific value of t. And so we can use that to solve for the unknown constant. So velocity at time 0, we know is I, 1, 0, 0. And we know from the integral that when we plug in t equals 0 into that, we get sine of 0 plus c1, which is just, what is sine of 0 plus c1? What is sine of 0? Right, it's just 0 plus c1, which is c1. E to the 0 plus c2 is 1 plus c2. And 1/2 times 0 squared plus c3 is just 0 plus c3, so c3. And so now we can solve for c1, c2, and c3. c1 is going to be what? What is c1? It's 1. You just equate components, so 1 equals c1. 0 equals 1 plus c2, so c2 is -1. And 0 equals c3, equating third component, so c3 is 0. So our velocity function, plugging in the values for c1, c2, and c3, is sine of t plus 1, which we said was c1, e to the t minus 1, which we said is c2, and 1/2 t squared plus 0, which we said is c3. Okay. So now that we have a definite function for velocity at all times t, we integrate that to find position. So do the same process all over again. So position is the integral of velocity, which we said was sine of t plus 1, e to the t minus 1, 1/2 t squared. Oops. So we do the same thing. We take the indefinite integral of each component. What do we get when we take the indefinite integral of sine of t plus 1? What do we get?
Negative cosine t plus c1.
Right. So negative cos t plus some unknown constant. You can call it c1 if you like, or d1 if you don't want to get it mixed up with the other, but I'm just going to call it c1. So do the same thing. E to the t minus 1, we take the indefinite integral. We get e to the t minus t plus some unknown constant. And then 1/2 t squared, take the indefinite integral. We get 1/6 t cubed plus some third unknown constant. So we have our unknown constants. Same thing, we use the initial position. We know r at time 0. We use that info to solve for the unknown constants. So position at time 0 is k, which is 0, 0, 1. And then plugging in t equals 0 into the integral we just took, we get -1. So negative cos t plus c1 becomes -1 plus 0 plus c1. So -1 plus c1. E to the 0 minus 0 plus c2, which is 1 plus c2. And then 1/6 cubed plus c3. So we get 0 plus c3. So c1 is what? What are c1, c2, and c3? So we get 1 for c1, and we get -1 for c2, and we get 1 for c3. So plugging those in, we get our full position function. We get negative cos t plus t minus 1, which was our c1, e to the t minus t. Oh, sorry, no, plus 1 was c1. Sorry, my bad. Plus 1, e to the t minus t minus 1. And then we get 1/6 t cubed plus 1. And that's our position. It's really simple if you understand the process here. You're just taking the indefinite integral and then using what you know about either the velocity if you're at the velocity, or the position if you're at the position at a given time, usually time 0. Then you can use that to solve for the unknown constants. Confused where I get the equation to plug c into? So you're confused about this So like this indefinite integral part, oh, wonderful. So this indefinite integral part or this next bit?
The second one.
Okay, so that is, we're given that in the problem. So we're told the acceleration function, and then we're also told the velocity at time 0 and the position at time 0. And so the velocity at time 0 we use in the first step when we go acceleration to velocity. So when we integrate acceleration, we get velocity, but we have these unknown constants. But we're told what velocity is at time, a specific time. We know that that is I, which is 1, 0, 0. And so we know this is our velocity function here. And so we plug in t equals 0 into that. And then that gives us something in terms of the unknown constants. And since we know what it has to be, 1, 0, 0, you can solve, equate each component to solve for the unknown constants. Does that clear that up? Yeah. Okay. So that's relatively straightforward. So let's look a little more in depth into acceleration. Okay. Okay, so in words, what is acceleration in relation to velocity? Acceleration is what? A velocity.
The rate of change to time.
Right, so it's the rate of change of velocity. So how can velocity change? Well, there are a couple different things that can happen, right? So velocity can obviously change. If you're just going in a straight line, velocity is changing if you are either speeding up or slowing down, right? So acceleration so it takes that into account. So it measures change in speed. Or I would say it involves change in speed. So if your speed is changing, then you're accelerating, right? Or your velocity is changing. So measures change in speed, but also, right, you could be going the same speed, but if your direction is changing, your velocity vector is changing also. So you're still accelerating, even if you're going the same speed, but you're going around, say, a circle or something like that. So if you're changing direction, you're also accelerating. So in fact, there's a way we can break down the acceleration vector, which takes both of these guys into account. So So recall our unit tangent vector. Remember, that's just r prime of t divided by magnitude r prime t. So r prime of t is just our velocity, and magnitude r prime t is our speed. And then the normal component, or sorry, not the normal component, the unit normal vector. Remember, that's just t prime of t over magnitude t prime of t. So from this, we know that capital N's a normal, the unit normal vector. So remember, the unit tangent vector is just the unit vector pointing in the direction of movement, right? So it's pointing in the direction of velocity, but it's just the unit vector. And the unit normal vector is the orthogonal to the unit tangent vector, and it's pointing in the direction that you're turning towards. Okay. So rearranging this guy here, we know velocity is just speed times the unit tangent vector. So taking derivatives, we know acceleration is the derivative of velocity so it's the derivative of speed times the unit tangent vector. And then using our product rule, we get that it is the derivative of speed times the unit tangent vector plus the first times the derivative of the second. So speed times t prime of t. And we know, we said this last time, t prime of t is the velocity times the curvature times the unit normal. You don't need to remember all of this explicitly, but wait. Okay, that is really hard to tell what is going on there. So this is a kappa. So velocity times curvature times unit normal. And so we have acceleration is, so v prime of t, the change in speed, right, times a unit tangent vector. So it's measuring how in the direction of travel that you're going, are you speeding up or slowing down? So that's the speeding up or slowing down bit. And then it also measures this other thing times the unit normal vector, which the unit normal vector points in the direction of, points in towards the change of direction. It's kind of a confusing way to put that, but. So times, now let me put it this way. The speed squared times the curvature. So this is not as clear what this means here, but speed squared times curvature times the unit normal vector. And I'll write this again here. So acceleration, we can break it up into components. We have the tangential component. which we call a sub t, and we have the normal component, which we call a sub n. And then we have, so the tangential component is the change in speed. So just a reminder, that v of t is speed. And the normal component is the speed squared times the curvature, which is less easy to understand what's going on there, but okay. I'm gonna go ahead and say no, because I know it's on the exam, and this is not, nor has it ever been on an exam, but it will be in the homework. So I'm going over it. The important bit is what we talked about at the beginning, knowing how to go from acceleration to velocity, or velocity and then to position. This stuff is components of accelerations on the homework, but it's not something you necessarily need to have memorized. I would say no. Okay, so a couple formulas, because yeah, I understand this is kind of a lot here. So the tangential component of acceleration is basically just your acceleration dot the unit tangent vector. Right, it's just like components of your vector, your I, j, and k components. If you want to find the I component of a vector, you dot it with I. You want to find the j component, you dot it with j. You want to find the k component, you dot it with k, etc. So same thing here. So that's a dot t. Well, t is just r prime divided by magnitude r prime, which is v divided by magnitude of v. So this is just a dot v over magnitude v. And the normal component is technically a dot n, but that's not usually the way we find it. So it's going to be the square root of magnitude of a squared minus the tangential component. Take the absolute value, square it. So if you want to know where this one comes from, it's because the magnitude of a squared is just a dot a. And when you do this, because t and n are orthogonal, you just get absolute value a sub t squared plus absolute value a sub n squared. Okay. So these two formulas we're going to use very, very quickly, and a problem to decompose acceleration into components. So suppose we know R of t for a curve. So we parameterize a curve as t squared 2t natural log of t. I gives position on curve at time t. So first, let's find the acceleration. And at time t equals 1/2, we're going to decompose acceleration into components. And we're going to find the curvature. Okay, so first, let's find acceleration. That's easy. We just take the derivative twice. So we know the velocity. We take the derivative once. So t squared becomes 2t. 2t becomes 2. Natural log t becomes 1/t. And so then taking the derivative of that, we get the acceleration is 2t becomes 2, 2 becomes 0, 1/t becomes negative 1/t squared. Okay. So that's acceleration for all times t. For the next bit, we're going to be using t equals 1/2. So we're going to look at this stuff at time equals 1/2. So what we're going to do is we're going to write acceleration like this. We're going to write it as something times a unit tangent vector, which we need to figure out what that is, plus the normal component times the unit normal vector. We need to figure out what that is. Okay. So let's figure out what all of this is at time 1/2. Well, let's just do acceleration for now, and then we'll figure out what we need. So acceleration at time 1/2 is, so plugging in t equals 1/2, we get 2, 0, negative 1 over 1/2 squared. So negative 1 over 1/4, which is negative 4. Okay. So we have negative 1, whoops, sorry, no, 2, 0, negative 4. So we need to find the tangential component. We need to find the unit tangent vector. We need to find the normal component. We need to find the unit normal vector. Okay. So the unit tangent vector is easy enough. So that at time 1/2 is just velocity at time 1/2 divided by magnitude of velocity at time 1/2. And we happen to know velocity at time 1/2. So velocity at time 1/2 is 2 times 1/2, which is 1, 2, 1 over 1/2, which is 2. And so magnitude 2 and 2 is just 3. So we get 2/3, 1/3, 2/3. Oh, sorry. No, 1, 1, 2, 2. Sorry, I'm moving very quickly here, and these are sort of complicated formulas. Kind of got to do an example here, though. So hopefully you can rewatch this, and this will make more sense upon second viewing. Okay, so we have our unit tangent vector. We need to find the tangential component. Well, we're going to use the formula I just gave back here. So the tangential component is just a dot t. And we know a and we know t. At time 1/2. So a is 2, 0, -4. And t is, we just found out, 1/3, 2/3, 2/3. So we take this dot product, we get 2/3 plus 0 minus 8/3. So we get -6/3, which is -2. Okay. So then we can find this bit here, the a dot n dot n, because we know a and we know a sub t times t. So that is a is 2, 0, -4. And a sub t is -2. And t is 1/3, 2/3, 2/3. And so we get 2 plus 2/3. So that's 8/3. And then 0 plus 4/3 is 4/3. And -4 plus 4/3 is -8/3. So we want to write that as something times a unit vector. And to figure out what that unit vector is, we just divide by, find out the magnitude, basically. Where do we get the -2 from? From this formula here, we know a sub t is just the dot product of a and the unit tangent vector. And we found out what the unit tangent vector was And so we know what A is, we know what the unit tangent vector is, we take the dot product, that's the -2. That's a tangential component of acceleration. Okay, so unit normal is just this vector divided by the magnitude. And my apologies, I'm really running through this, but the magnitude is 4 here, which you can calculate. And so we just get the unit normal is going to be 2/3, 1/3, -2/3. And so A sub n is going to be 4. Okay, so we want to find the curvature at time 1/2. And so we know our formula, from our formula, we know the normal component of acceleration is the speed at time 1/2 squared times the curvature, oh my God, at time 1/2. And so we know the curvature, just divide both sides by the speed squared. Sure. This is really a matter of sort of, you're not going to have these memorized, but you do need to be able to sort of go through the formulas, which you may not fully understand, but you need to figure out how to write down everything and learn what you need to figure out, and then go refer to the formulas to figure said things out. So the curvature is going to be, let me write this down here, rearranging this guy, dividing by the speed squared. The curvature is going to be A sub n, which we said is 4, divided by the speed at time 1/2 squared. And so the speed is magnitude of velocity. Velocity was 122, and so the magnitude of that is 3. And so the curvature is 4/9. I wish I had more time to go over this, but unfortunately I do not. Any questions about that?
So is A sub the normal vector just the magnitude of?
Yeah, so yeah, okay, so A sub n is sort of, yeah, the bit of acceleration pointing in the direction of the normal vector. So acceleration you can write as the tangential component times the unit tangent plus the normal component A sub n times the normal vector. So what we did initially is we have a nice formula to find. It's easy to find the unit tangent vector. That's fine. Easy to find the tangential component. And then we are sort of working backwards to find each of these guys together. So we know A sub n times n, if we already know A sub t and we know t. If we subtract that from both sides, we get A sub n times n. Well, we know n is a unit vector. So if we do A minus the stuff we subtracted, we get a sub n times n. And to figure out what n is, you just turn that vector into a unit vector. So the magnitude of that is going to be a sub n, and then n is going to be the unit vector pointing in that direction.
Okay, thank you.
Any other questions? Okay, so yes, I'll be sending out some emails with a fair bit of information in the next couple days, but make sure to this weekend go over the practice problems that are, once again, in Canvas under Files, under the exam review questions. Do those ones first, and then I would do, it's also going to be very helpful to do the practice problems on the Math 230 website. Just Google Math 230 PSU. And so you want to look at the ones from exams 1 and 2 there, because we had twice as many exams last semester. But yeah, anything else? If not, I have a great weekend. I will see you guys on Monday. And yeah, take it easy.